Good morning. Okay, so I have one or two things that I really wanted to show you guys today, and then whatever time is left over, we can spend reviewing for the test on Wednesday. I don't want to waste any time, so I'm going to move quickly to show you those one or two things that I really wanted to show you. Oh, it looks like I need to reopen this though. So today's our last day of lecture. It's our last day of normal Calc 2, and I just wanted to, again, let you guys know how proud I am that you've hung in here and really worked through it all semester. It takes a lot of heart to not give up in a class that has as much tough content as this does. So wherever you are, however you're feeling about the material, just know that I'm genuinely proud of you for the work you've done this term. All right, that's the doc cam up, so let me go ahead and share the screen. There we go. All right. So a few things for today. I have a treat related to power series. A few more polar graphs. And we're going to talk about areas in polar coordinates. So this little treat at the top related to power series, this is something that I feel obligated to show every Calc 2 class I teach. It's a really cool thing. And if we had a little bit more time in the semester, then I would give you an assignment that would allow you to explore it on your own. But because time is limited, today is our last day of class, and we do still have material to work through. It's not a totally free day. I'm going to go ahead and show you this little treat related to power series first. Throughout the semester, you've heard me allude to something special about exponentials and trig functions. Okay, you may have noticed that mathematicians, math teachers of your past, or physicists all kind of treat these three functions with the same sort of reverence, meaning like we love them all about the same. E to the x, cosine x, and sine x. There's a beautiful, beautiful connection between these things that is really only justifiable through power series. The first time I saw this, I just didn't believe it. I'll tell you that. I just did not believe it. It was shown to me, and I said, no, 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 no. That can't possibly be true. Okay, so exponential functions, a little bit tricky to define for weird numbers. I know what it means to take a number and square it and multiply that number by itself. I know what it means to take that number and raise it to like the 3/2 power. That means a cube it and then take the square root. But what does it mean to say I'm going to take a number and raise it to a complex number? What does it mean to raise the number e to say like I times 2 or I times 3, where I here is the square root of -1, the thing you've always known? No doubt some of you have seen this, but also probably some of you haven't. That's the shocker. And it's true. E to the I theta is straight up equal to cosine theta plus I times the sine of theta. This has some really bizarre consequences. It'll tell you how to take the natural log of -1, for example. What the fuck? It'll tell you what, e to the I pi is. Turns out to be -1. I know it's weird too. E to some stuff is always supposed to be positive. So a lot of this, if you spend some time thinking about it, you'll realize this thing breaks a lot of the rules that you learned about exponentials. But it does more than that. It also gives us a new way of thinking about sine and cosine. And if you move further in any fields even tangentially related to harmonic analysis, especially quantum physics, this is hugely important. Proof. All right, I just can't let you out of Calc 2 without showing you this. It's that beautiful. It's very, very special. But it's all about power series. E to the x, remember, is the sum from 0 to infinity, x to the n over n factorial. These are power series that you need to know. Sine x as a power series is the sum from 0 to infinity, -1 to the n over 2n plus 1 factorial times x to the 2n plus 1. And cosine x is the sum from n equals 0 to infinity, -1 to the n over 2n factorial times x to the 2n. So far, everything here is stuff that we know. That's why I'm saying recall. Now, how am I going to use these to prove this? Well, I'm going to take the power series for e to the x, and I'm going to replace x by I times theta. Just like we did in a bunch of those homeworks, those last couple power series homeworks where you had to sum a series by plugging something in for x in a power series. I'm going to do that same trick here. So this will give me I theta to the n over n factorial. And I'm going to write this out. That's I theta to the 0 over n factorial. I theta to the 0 over 0 factorial plus I theta to the 1 over 1 factorial plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus, and it keeps going, I theta to the 4 over 4 factorial plus, and so on. Anything to the 0th power is 1, and 0 factorial is 1. So the first term of that series is 1. Plus I theta to the 1 is I times theta. And I'll put it over the 1 factorial still. Why not? We can put this over the 0 factorial still. Plus I theta squared. That's I squared theta squared over 2 factorial, and we'll do the same, plus I cubed theta cubed over 3 factorial plus I to the 4 theta to the 4 over 4 factorial. The next term is I to the 5 theta to the 5 over 5 factorial, and I'll do one more. The next term is I to the 6 theta to the 6 over 6 factorial, and it goes on. Now, you may or may not know this about powers of I, but they cycle. I to the 1 is I squared is -1, because I is the square root of -1. I cubed is I to the 4 is +1. So if I compute the powers of I here, I get 1 over 0 factorial plus I times theta over 1 factorial. I squared is -1, so this is -1 times theta squared over 2 factorial I cubed is negative I. So this is negative I times theta cubed over 3 factorial. I to the 4 is positive 1. So this is theta to the 4 over 4 factorial. I to the 5, let's think about this. This is I times itself 5 times. So that's I times I, negative 1, times I, another negative 1, times I. So that's negative 1 times I. That's positive I. So that's plus I, theta to the 5 over 5 factorial. I to the 6 is this thing, I to the 5 times I. So I times I, that's negative 1. So this is going to be negative theta to the 6 over 6 factorial, and so on. And the cool thing here happens if you group the real pieces and the non-real pieces. So the real pieces here, this, 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 and this. So I'm going to give myself some more space. I'll continue over here. That's 1 minus theta squared over 2 factorial. I'll write the 1 over 0 factorial. Why not? 1 over 0 factorial minus theta squared over 2 factorial plus theta to the 4 over 4 factorial minus theta to the 6 over 6 factorial, and so on. And then plus, everybody else has an I in it. I'll factor the I out, and we get theta over 1 factorial minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial minus, and so on. This is the power series for cos theta. This is the power series for sine theta. So this really is cos theta plus I times sine theta. And that's it. That's the proof. So e to the I theta really is cos theta plus I times sine theta. It's a fact that comes from power series. And there's no other nice way to prove it, certainly not with the skills that we have in this class, and not with anything that I'm aware of that goes anywhere near as fast. It's thought of always as a fact about power series. Some really wild consequences of this. One of them you've seen on a t-shirt. And when I do this in class, I usually wear that t-shirt. I wore it yesterday, so it's dirty today. If I take e and I raise it to the I times pi, then I would get the cosine of pi plus I times the sine of pi. Well, the cosine of pi is -1, and the sine of pi is 0, so e to the I pi is -1. True story. If you take pi, multiply it by I, then raise e to that number, you get -1. Another way of saying this is e to the I pi plus 1 equals 0. And this has a few different names. Usually Euler shows up in it somewhere. Euler's formula or something like that. Euler's identity. It's just a beautiful statement that to some people is especially significant because it involves pretty much all of the important constants in mathematics, e, I, pi, 1, and 0. Those are sort of all the super special numbers that keep showing up in our study of mathematics. And also all the important operations. You've got addition, equality, exponentiation, multiplication. So this is a very pretty thing. So sometimes called Euler's formula or Euler's identity. This statement up here, the original statement, is usually called Euler's formula also. Named after the man Leonhard Euler, who of course did huge amounts of work. Yeah, basically, yeah, it's nuts. This trivializes so many really challenging things. Another fun thing, consequence one, here's another fun thing. What could possibly be the natural log of -1? You know that the natural log function's domain is just 0 to infinity. You can't plug negative numbers into a natural log. Or can you? Begin with e to the I pi equals -1 and take natural logs. Then you'll get the ln of e to the I pi equals the ln of -1. Well, the ln of e to anything should just be that thing. That's the definition of ln. So I times pi is the ln of -1. Another big shock, right? This is very strange. This should scare you. This breaks all the rules. Another fun game you can play. This will be where I'll stop with this little treat. Ever wonder what I to the I might be? So you take the imaginary unit I, the square root of -1, and you raise that to the power of I. So this is looking about as complex numbers can be. The shock here is that this is a real number, and it is. Recall that in general, a to the b, that's the same as e raised to the natural log of a to the b, because anything e to the log of stuff is just that stuff. But now by rules of logarithms, this is e to the b times the natural log of a. So I to the I is e raised to the I times the natural log of I. Well, I need to know what the natural log of I is to proceed. Since e to the I theta is cos theta plus I sine theta, if I plug in pi over 2, e to the I pi over 2 will be cos of pi over 2 plus I times the sine of pi over 2. So e to the I pi over 2, cos of pi over 2 is 0, sine of pi over 2 is 1, is I, which means that I pi over 2 is equal to the natural log of I. Take natural logs on both sides again. So all of this is like side work. So now the natural log of I is I pi over 2. So this is e to the I times I pi over 2. And now I times I is I squared, that's -1. So this is e to the negative pi over 2. So I to the I, this thing, is equal to e to the negative pi over 2. It's a real number. I can go on and on for days. There is so much really shocking stuff that falls out as a consequence of this. All right, what we just discovered is that I to the I is really the real number, e to the negative pi over 2. So I'll leave it here. Hopefully, if you've been at all interested in what's been going on in the last like 4 math classes you've taken, this stuff should all be kind of making your stomach curl up and making you go, what the fuck? That's the correct reaction. If that's what you're feeling, that's good. That's okay. And I invite you to explore consequences of this further. A to the I theta is cos theta plus I sine theta. One of the most important relations in all of mathematics, specifically in complex analysis, which is hugely important to quantum physics, electromechanics in general, really everything. Even number theory, huge applications in number theory. Okay, so that's our treat. That is our like end of semester treat that I'm really excited to show you guys. And I'm sorry I couldn't spend more time with it. But that's it. You know, this is one of those happy things you get at the end of Calc 2 that totally impossible before Calc 2. We had to build up all semester to get to power series. And then this is probably the most breathtaking consequence of power series that's accessible to us at this point. Another thing we had to do today is look at a few more polar graphs. So I'd like to do that now. There's a family of polar graphs that we haven't seen. We looked at cardioids last time. We saw some circles. Another interesting family of polar graphs that are pretty important are these rose graphs or petal graphs. And if you looked at the things that I posted to the modules following Monday's class, you see some examples, but I want to go through 1 or 2 more examples where we're graphing these things by hand ourselves. So returning to polar graphs, let's sketch R equals sine of let's do 2 theta first. So remember, we always begin with the Cartesian graph. I'll come up here and mark this as +1. I'll come down here and mark this as -1. And we want to make sure we go all the way out to 2 pi. Because we need to know what happens as you walk all the way around the circle in the polar setting. Now, sine of 2 theta, this has twice the angular momentum, or twice the angular velocity that regular sine has. In other words, the period here is 2 pi over this number, which is pi. So we'll go through 2 full periods of this function between 0 and 2 pi. We'll have 1 full period out to pi, and then another full period between pi and 2 pi. What that means is that sine, you know, he starts here. He needs to get through a full period by the time I get to pi. So this is pi over 2, and these little marks are multiples of pi over 4. This is 3 pi over 2. So he's going to jump up here right away, come back down here like this. So here's 1 full period. And then he's going to jump back up here, come back through here, down to here, and then back up again by the time we get to 2 pi. So sketching this graph shouldn't be intimidating, right? This is something that we learned how to do back in trigonometry and hopefully never forgot, but you may need to recall the formula for the period. So remember sine of omega t or omega theta has period two pi over omega. The same is true for cosine. So now we'll want to translate this into a polar graph. The max amplitude here is 1, right? The largest R ever gets here is 1. The amplitude is 1. So I'll go ahead and come out here and mark this as 1. And I'm going to add in some helper lines. This is theta equals pi over 4. This is theta equals 3 pi over 4. Theta equals 5 pi over 4. And this one would be theta equals 7 pi over 4. Remember, this is pi over 4 here, halfway between 0 and pi over 2. So what's going on? R starts out at 0. And as theta increases from 0 to pi over 4, R increases from 0 up to 1. So I have the polar point 1 comma pi over 4 here. And as my little arm is spinning around, my little dude is going to have to run out from the origin all the way to that tip there. So as theta spins from 0 up to pi over 4, R is doing something like this. And then as theta advances, as I rotate past pi over 4 towards pi over 2, R starts coming back in. So if I were to look just a little bit further, if I were to rotate just a little bit past pi over 4, R should have come in a little bit from here to like here. So this is starting to do something like that. And by the time I rotate all the way up to pi over 2, R should be all the way back at 0. So I should come in here tangent like this, arriving back at the origin. Here's where things get a little funny. From pi over 2 to pi, normally I would be drawing over here, right? This is theta equals pi over 2. This is theta equals pi. But because R is negative, remember R being negative means you have to reflect all those points through the origin. So normally from theta equals pi over 2 to theta equals pi, I would be drawing something over here because this is that range of theta. But because R is negative, I'll be drawing over here in the region that's reflected through the origin from that. So as I advance theta past pi over 2, if I imagine my little arm rotating a little bit past pi over 2 like this, R is poking back out from the origin, but it's doing it in the negative direction. So let me see if I have a thing I can use here. So I rotate a little bit past pi over 2. If R were positive, I would be drawing over here, right? But since R is negative, I'll actually be drawing over here. And as we rotate around, once I get to this guy, which is 3 pi over 4, R will be all the way out at -1. So here's 3 pi over 4, +1. Here's 3 pi over 4 with a radius of -1. So at this point, I'll label these. This is 1 comma pi over 4. This guy is -1 comma 3 pi over 4. And what happens there is we poke out like this. And that is this region. So if you want to, you can add some color here in a way that may be helpful. I like to color a region of this graph and color the corresponding bit over here to help us see which part of the graph comes from which part of the rectangular graph. Now, as we rotate past 3 pi over 4 towards pi, r starts to come back in. That's going to correspond to this. As we rotate past pi, as we keep going here, r is positive again. So no more funny business of reflecting through the origin. We're going to come all the way out to a max of 1 when r is equal to 5 pi over 4. So we're going to come out here to 1 comma 5 pi over 4. And that's going to look like this. And then, as we rotate past 5 pi over 4 towards 3 pi over 2, my little guy is running back in along that arm. So he's going to do something like this. And when he gets to 3 pi over 2, once my arm is facing straight down like this, r will have run all the way back into the origin. And just looking at the symmetry of the polar graph, you can kind of guess what's going to happen. Each one of these bloops here corresponds to one of these bloops here. And this last little guy normally would have us drawing in this quadrant, because these are the angles 3 pi over 2 up to 2 pi. But r is negative here, so rather than drawing in this quadrant, we'll be drawing in the reflected quadrant over here. This is 7 pi over 4, and we have the polar point negative 1 comma 7 pi over 4 that we know will be on our graph, and he's going to be arrived at like that. And then as we come past here to here, we will be running back into the origin. So these are called petal graphs or rose graphs. And there is a relationship between the number of petals and the number inside your sine or cosine function. The new bit of material I'm going to teach you today is how to find the area of one of these things. But I wanted to go through an example with you. I invite you to fiddle around in Desmos. I'm spending some time here trying to find really good resources for you guys, but it's actually pretty limited. I'm actually researching something here, how I can generate animations for you using Python, but it's not going to be something that will come together quickly. So let's just look at a few simple examples. Here's the one we just did. Oh, and I'm zoomed way out. Let me zoom back in. All right. So what happens if I change this number inside here from a 2 to a 3? Oh, we'll have 3 petals. If I change it from a 3 to a 4, I've got 8 petals. 4 to a 5, 5 petals. So if the angular velocity, the number on the inside of the sine function, like sine 2 theta, 3 theta, 4 theta, 5 theta, if that number is odd, then you'll have that number of petals. But if that number is even, you'll have twice that number of petals. And you might ask, well, what about cosines? Cos theta itself, just like sine theta itself, is a circle. But if I start doing this, then the same sort of thing happens. I get these petal graphs, only you'll notice the cosine petal graphs are oriented a little different than the sine ones. Cos 2 theta looks like this. The angular velocity is even, so I have twice that number of petals. Cos 3 theta, here its angular velocity is odd, so I have exactly that number of petals. Cos 4 theta even, so I'll have 8 petals. This time it's just a range like the cosines. So that's these petal graphs. They're neat. And if you go back into your trig book, the calculus book unfortunately doesn't have a lot of examples here for us to play with, but if you go back to your trig book, the section on polar graphing, you'll see a table that actually outlines a bunch of common polar graphs and their equations, kind of telling you how you can know what to expect based on this. But the real skill I'm interested in you guys learning is the process of going from this graph to this graph. And I'll tell you right now, on your final, there will be a problem that requires you to draw a Cartesian graph from a function like this, and then take the Cartesian graph that you draw and move it into a polar graph like this. It's not a terribly hard thing, but it's not completely easy either. You will have to practice it a little bit. It's not just formulas. It does require a little bit of conceptual thinking. So spend your time practicing that before the final. The last bit of truly new information I need to share with you guys is how to calculate areas in polar coordinates. So that's what we're going to do next. So for example, how do I find the area of this petal? You might think that because this petal comes from this part of the Cartesian graph, that the area of this region is the same as the area of this region. That's not true. So let me derive for you now the formula for areas. There's one sort of little preliminary here, and that's the area of a sector of a circle. Now this is something that that I do have for you in the modules. Something that we did back when we learned about trig sub. I specifically put it in there so we can refer back to it here. Area of a sector of a circle. What is it? No, it's not. Okay, I'll have to add this. It might be in here. Here it is, area of a sector of a circle. All right. So it's not a terrible trig sub problem to cook up the area of a sector of a circle. I'll spoil it for you. The area of a sector of a circle is 1/2 r squared theta. So we'll take that as axiomatic. This is section 10.4. And it's the last bit of new material I teach you guys in Calc 2. There's other ways to get the area of a sector of a circle. The trig sub thing is cute, but I'll walk you through this in a way that doesn't require trig sub. It can be done much faster. Okay, so if I have a sector in here where the angle is theta, what is this area? So the radius is r, the radius of my circle is r, and this angle in there is theta. You know that the whole circle has area pi r squared, right? And you know that the area of the sector here should be a linear function of theta, right? If theta is half of the circle, pi, then you should get half of the area. If theta is a quarter of the circle, pi over 2, you should get a quarter of the area. So the area of a sector A is the unique linear function that's equal to this when theta is 2 pi. And that's 1/2 theta times r squared. You can try it. Plug in theta equals 2 pi, the 2's cancel, you get pi r squared. Plug in theta equals pi, you get 1/2 pi r squared, which is half the area of the circle. It's the only thing that makes sense. And it's the unique linear function that is equal to pi r squared when theta is equal to 2 pi. So this is our little preliminary. Now suppose you've got a curve. R equals, we'll call it f of theta. Actually, let me just call it r of theta. That'll make life nicer. I'm sorry for the notation change. R equals r of theta. And you want to find the area, so maybe that curve looks something like this. I don't know, some random bullshit. This is the polar graph. And you want to find the area between, say, some angle down here and some angle up here. So maybe this is coming from theta equals alpha, and this is theta equals beta. And you want to find this area in here. Well, the polar point here is r of alpha, comma, alpha, and the polar point here is r of beta, comma, beta. And the trick is to just chop this up into a bunch of little pieces. So it's kind of like a Riemann sum. You partition and then in each one of these little partitions, you approximate the area using the area formula for the sector of a circle. You pretend like this is a circle of radius r. So this, we partition the theta interval alpha beta into n equal length subintervals. With delta theta being beta minus alpha over n. So alpha would be theta 0. And this point up here, I would say it's coming from theta 1, so this would be r of theta 1, comma, theta 1. This would be r of theta 2, comma, theta 2, and so on. And then on each one of those little subintervals, I pretend like this is really just a circle. All right, I pretend like r is constant. On each subinterval, approximate the area as a sector of a circle. So for example, in here, I'm going to pretend like this is a sector of a circle. It's not. It's off by a little bit. But on each one of these, I pretend like this is a sector of a circle. Okay, those are your like Riemann rectangles. They're not rectangles here, they're little circular sector areas. I call the area here A1, A2, A3, and so on. This last guy is AN. Then the total area is approximately a1 plus a2 all the way out to an. And each ai, this is the area of a sector. So I can approximate it using the formula 1/2 theta r squared. So that's 1/2 delta theta, because each one of these is delta theta wide, like that's the angle between each of these little regions is delta theta, times r of theta I squared. Because this is r of theta 0, r of theta 1, r of theta 2, the radius of each of the little circular sectors I'm thinking of is coming from my function. So this approximate area can be written as the sum I from 1 to n, 1/2 delta theta times r of theta I squared, which is a Riemann sum. You move the delta theta off to the end, and you recognize that as a Riemann sum for the actual area, which is the integral from alpha to beta, 1/2 r of theta squared d theta. So if you want to find the area enclosed by a polar function, by a polar curve, you don't integrate the function r, you square r, then multiply by 1/2, then integrate that. Let's try an example. This guy that we graphed earlier. Suppose I want to find the area of just one of these loops. The tricky stuff here is figuring out which theta values correspond to the region you want. If I asked explicitly for this guy's area, you would have to realize that he's not coming from theta equals 3 pi over 2 to theta equals 2 pi, even though those are the theta values that we normally think of as coming from this region. Remember, and that's why I colored this part of the graph, he actually came from theta equals pi over 2 to theta equals pi, because r was negative there. But let's say I'm going after this loop. By symmetry, I could do any of them. What theta values gave me this first loop here? I'm going to require some feedback from you guys. Good, yeah, 0 to pi over 2, right? This was theta equals 0. This is theta equals pi over 4. And it came in here at theta equals pi over 2. So that would be integral 0 to pi over 2, 1/2 r of theta squared. R of theta here is sine 2 theta, so that's sine of 2 theta all squared d theta. This would be the integral I had to do. So you can pop out the 1/2. You're left with integral 0 to pi over 2 sine squared of 2 theta d theta. And that's not a terribly hard integral. Does anybody remember how to handle that integral? Yeah, because the power of sine here is even, and there's no odd power of cosine to work with, I have to use the half angle identity. So that's 1/2 integral 0 to pi over 2. Half angle identity for sine says sine squared of x is 1/2 times 1 plus cosine of twice whatever's in here. Now that's going to be 4 theta. The identity I'm using is sine squared x is 1/2 1. Ooh, this should be a minus, shouldn't it? Yeah, sorry. 1/2 times 1 minus cos 2x. The other similar one, the one that I confused that with there for a second, is cos squared, which is 1/2 times 1 plus cos 2x. So anytime you bump into an integral of a pure even power of sine or cosine, this is the only attack. And from here, it's not bad. I can pop this extra 1/2 out. So I'll have 1/4 integral 0 to pi over 2, 1 minus cos 4 theta. And now I can cook up my antiderivative. That's theta minus sine 4 theta over 4. And we evaluate this from 0 to pi over 2. At the lower bound 0, I have 0 minus the sine of 0 over 4. That's 0 minus 0 over 4. That's definitely 0. So the only interesting stuff comes from the upper bound, where I have 1/4 times pi over 2 minus the sine of 4 times pi over 2, all divided by 4. 4 times pi over 2 is 2 pi. Sine of 2 pi is 0. So this is 0. And I get 1/4 times pi over 2, which is pi over 8. So that's it. The area enclosed by one loop of that curve is pi over 8. Again, the challenge with the area problems in polar coordinates is making sure you know which part of the graph corresponds to which theta values, because it's not always the obvious thing. All right. So with that, guys, I am done with things that I need to show you. And I'd be happy to spend the rest of class working whatever sort of problems you would like. So is there anything from the study guide or the most recent few homeworks that you guys would like to take a look at? Could be power series stuff, could be graphing stuff, could be whatever you want. Sure. Is there any particular power series problem you want to look at? I can pull up the study guide. Differentiation, I didn't have one in mind. Okay, let me see if I have anything handy. Did I give you any problems like that in your study guide? You have to differentiate a power series. I need to refresh. Taylor and Maclaurin series? Sure. All right, let's see what we've got here. So what is a power series? Find the radius of convergence, find a power series. I don't think any of those power series problems I put in your study guide require you to differentiate any power series, but we can take a look at one of each here, sort of thing. So what would be a good example? Most of these are related to each other through kind of obvious things, so it's a little bit tricky to come up with a novel problem. So let's try this. Okay, 1, let's look at number 20 from homework 13. I'll move to that next. Well, actually, let's take a look at that first, make sure it's not something that we could fold together with this. Although I don't think it is. Okay, yeah, we'll come back to that. So, so I think from 11.9, which is the first section where you had to find power series for functions, these are sort of the hardest ones. Yes. Yeah, Nick, it'll be up tonight. Where you need to differentiate another known power series to get your power series. These are tricky for a few reasons. First, you have to come up with the relationship between the known series and the series you want. So what I would see when I look at this 1 over 1 plus x squared, this looks like, let's see here, f of x looks like what I would expect to get from differentiating 1 over 1 plus x. So this is my guess. Now I'll actually differentiate this to check. If I take the derivative of 1 over 1 plus x, I'll do it with the chain rule. That's the derivative of 1 plus x to the negative first. I get negative 1 times 1 plus x to the negative 2 times 1 by the chain rule. So this is negative 1 over 1 plus x all squared. Which means if I multiply both sides of this by negative 1, that negative 1 times d dx of 1 over 1 plus x is 1 over parentheses 1 plus x squared. So the function I want a series for is the derivative of this guy times negative 1. So I'm going to start by finding a power series for this guy, then I'll differentiate it, then I'll multiply by negative 1. So f of x, which is 1 over 1 plus x quantity squared, is negative 1 times d dx of 1 over 1 plus x. Which is negative 1 d dx 1 over 1 minus negative x. And I'm thinking here of using my geometric series trick. 1 over 1 minus r is sigma n from 0 to infinity r to the n. So 1 over 1 minus negative x is sigma n from 0 to infinity negative x to the n. So now this is negative 1 d dx sigma n from 0 to infinity negative x to the n. Before I can differentiate this series, I need to simplify the inside. I don't want a negative x to the n, I just want an x to the n. So, all right, this is negative 1 d dx sigma n from 0 to infinity. Negative x to the n is negative 1 to the n times x to the n. And this will be negative 1. Now I'll go ahead and differentiate. This will be sigma n from 1 to infinity, negative 1 to the n x to the n minus 1. That's what the derivative looks like. I had to bump the n equals 0 starting index from 0 to 1 because the series I'm differentiating here does have a constant term. This is 1 minus x plus x squared minus x cubed. So the 0 bumps up to a 1 because the series I'm differentiating does have a constant term. You may want to look back at your notes from 11.9. And then when I go to differentiate, it's just this piece that changes. X to the n differentiates to n, x to the n minus 1. It's a power rule. My last step is going to be to bring the negative 1 inside. So this will be sum 1 to infinity. Negative 1 times negative 1 to the n is negative 1 to the n plus 1. And then I have n x to the n minus 1. And that's it. That's your answer. Patanjali wanted to look at Taylor series problem. So there's a bunch of different ones, bunch of different problems that make use of Taylor's theorem. Are you thinking one where we build the table, Patanjali? Like find a series using the definition of Taylor series? Let me try a few things along those lines. First, let's use the definition of the Taylor series. To find the first, say, 5 terms of the series for f of x equals, what would be challenging? What haven't we done yet? Let me grab something from your book. It's just so many things to use. Power series, Taylor Maclaurin series. How's about, yeah, I mean, sine, cosine, binomial stuff. We've done all of these. Arctan, it's not exciting. Oh yeah, let's do 2 to the x. That'll be fun. Sure. So rather than finding the full Taylor series here, I just want the first 5 terms. The full Taylor series here we could find, but it would start out the same way. We're going to build a table. And the hint is that they said use the definition, right? If they said something other than use the definition, we might try to get sneaky and get this by modifying the series for e to the x or something like that. But our table has n, the nth derivative. We'll say centered at 0. So then fn of a goes here, which is fn of 0, and then cn on the very end. All right, let's see what we can find. When n is 0, if I don't differentiate at all, f is 0 of x, the 0th derivative, the function itself is 2 to the x. And if you plug in the center, 2 to the 0 is just 1. So C0 is 1 over 0 factorial. If n is 1, if I differentiate once, f1 of x, the first derivative, what is the derivative of 2 to the x? Who can help me out with that? What's the derivative of the function 2 to the x? It's not a power function, no. So if the power was constant 1, then I could do that. If this was like x to the 2, then I can use the power rule to differentiate. But this is an exponential function. This is why I chose this guy, just to see if we remember how to differentiate exponentials. You know, the derivative of e to the x is e to the x. The derivative of any other base exponential function is that function times the natural log of the base. Yeah, good. 2 to the x times the natural log of 2. Tanji's got it. So this fellow here is 2 to the x times the natural log of 2. So if I go plugging in 0, I'll get 2 to the 0 ln 2. Which is just ln 2. So C1 is the natural log of 2 divided by 1 factorial. Oh, sorry, this was n equals 1. If n is equal to 2, if I differentiate again, the second derivative, this ln 2 just comes along for the ride. So I'll get 2 to the x times ln 2 all squared. So at 0, that's going to be 2 to the 0 ln 2 squared, which is just ln of 2 all squared. So C2 here is ln of 2 squared over 2 factorial. When n is 3, the third derivative is 2 to the x times ln 2 cubed. So this fellow would be 2 to the 0 times ln 2 cubed. So C3 here is the natural log of 2 cubed over 3 factorial. And I can even say what this will be in general real quick here, though, because all we asked for was the first 5 terms. The fourth derivative would be 2 to the x times the natural log of 2 to the 4. So this would be 2 to the 0 times ln 2 to the 4. So C4 is natural log of 2 to the 4 over 4 factorial. So 2 to the x is approximately, the first 4 terms of this series would be C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4. This is the first 5 terms, which are 1 plus the natural log of 2 times x divided by 1 factorial, okay, plus natural log of 2 squared over 2 factorial, which is 2 times x squared, plus C3 is the natural log of 2 cubed over 3 factorial times x cubed, and then C4 is the natural log of 2 to the 4 over 4 factorial times x to the 4. So these would be the first 5 terms of the Taylor series for this function centered at 0, aka a Maclaurin series. Now, if you notice the pattern over here, you can go ahead and say what the full Maclaurin series is. Cn in general looks to be the natural log of 2 raised to the n over n factorial. So we could go all the way here and say 2 to the x is sigma n from 0 to infinity, natural log of 2 to the n over n factorial times x to the n. And if this looks similar to the e to the x series, that's good, right? 2 to the x and e to the x are similar functions. We expect them to have similar series. And it is, in fact, possible to get this series from the e to the x series by being clever. If you can write 2 to the x as e to the x times the natural log of 2, if you're willing to play those sort of algebra tricks. But for the purposes of this problem, this is what we were asked for. And it all came from this table. Questions about the table work or how we got to this answer here, the answer they asked for? Okay. So I think that leaves time for us to go back to homework 13 and look at number 20 that one wanted to see. That's this guy. Find the length of the loop of the curve here. All right, let's take a look at this curve. I'm going to plot this curve in Desmos. 12t minus 4t cubed, that's x. So let me get out of this. We'll go to a fresh graph. My x function goes in here. So that's 12t minus 4t cubed. I will go ahead and throw in the t slider here. And then my y function was 12t squared. Okay, so let's see if we can't get a feel for what this is by watching the point move around. There's the point. What's this thing doing? Oh, it's doing something weird. I'll zoom out a little more. I still can't see it. Oh, there it is. Nifty. So can you kind of see the curve? So they asked for the length of the loop of the curve, suggests that it should connect to itself. 12t minus 4t cubed. Yeah, okay. So let me get rid of the slider and see if we can give this a concrete picture. There it is. So what's meant by a loop of this? That's a tricky thing to interpret on its own. But I would say the loop there is probably, this piece here. So we need to figure out what t values correspond to this point. And we're going to integrate to find the length of this loop. So what is that point up there? Well, here, x is 0. We could actually figure it out just by setting the x to 0. That'll have several solutions. So we want to, I'll write this down, find the length of the loop and x of t equals 12t minus 4t cubed. Y of t is 12t squared. Okay. So having looked at the graph, we would have to look at the graph to get started here. And this is not an easy graph to draw by hand. I wouldn't expect you to be able to figure out what this graph looks like without plotting a bunch of points by hand, kind of a pain in the ass. We're using Desmos. So here I think it's appropriate to use Desmos. If you had all the time in the world, you could plot this graph by plotting points, but we don't have all the time in the world. Let's try to figure out what t values correspond to the start of the loop and the end of the loop. Notice here that at this point, x is 0, but also at this point down here, x is 0. So a few ways I could do this. The y values here seem to be unique, right? At this point, x is 0 and y is 36. So we can say the start and end of the loop is the point 0, 36. So to find our starting and ending t values, we solve x of t equals 0 and y of t equals 36. I expect a total of 3 solutions from the first equation, 2 solutions from the second. So we could just solve the second, but let's go ahead and do both. X of t is equal to 0 if and only if 12t minus 4t cubed is equal to 0. I can factor out a 4t here, and I'll be left with 3 minus t squared. All right, 12 divided by 4 is 3. 4t divided by 4t is t squared. So this is going to have the solutions t equals 0 and t equals plus or minus the square root of 3. On the other hand, y of t is equal to 36. It's true if and only if 12t squared equals 36. So that's the same as saying t squared equals 36 divided by 12 is 3. So t here has to be plus or minus root 3. So it's these t values that I want. The t equals 0 here is coming from the point at the bottom. This is the t equals 0 point. This t, you come in at negative root 3. Here's t equals 0, and then you leave, and t is positive root 3. So I'm going to integrate ds from negative root 3 to positive root 3. So the desired arc length is the integral from t equals negative root 3 up to t equals positive root 3 ds, where s is my little arc length element. Remember, ds is the square root of the x dt squared plus dy dt squared. That's that little Pythagorean thing times dt. So I need to cook up the x and y derivatives with respect to time. Dx dt, the derivative of the x function taken with respect to time, is 12 minus 12t squared. And dy dt, the derivative of the y function taken with respect to time, is 24t. So I'll square these, add them up, take the square root, and integrate. And this integral may be easy, may be hard. If we're lucky, there's a lot of cancellation. We'll have to FOIL this out, combine like terms, and see what we get. So I'll have the integral from negative root 3 to positive root 3, square root of. When I FOIL this out, 12 squared is 144 minus 2 copies of 12 times 12, which is, actually, no, it would be easier. No, we'll do it. So 12 times 12 is 144. So we'll have minus 2 times 144 t squared plus 144 t to the 4. That's that first piece. Plus 24, oh no, 24 squared, shit. So that's 2 times 12 is 2 times 144 t to the 4, or t squared. Okay, that is nice. We see that this term and this term cancel. I wrote 24t all squared like this so we could see that it would cancel with this. 24 is 2 times 12. Oh, wait. Did I do that right? No, those aren't going to cancel. Sorry, this should be a 4, shouldn't it? Yeah, 2 times 12 all squared is 4. 2 squared times 144, 12 squared. So they're not going to go away exactly. This is still going to be a little bit ugly. But it looks like at the very least I'll be able to pull out a factor of 12. So we'll have integral from negative root 3 to positive root 3. I'll write the square root in a second. 144. I've got minus 2 of these plus 4 of these. That'll give me plus 2 of 144 t squared. And then plus 144 t to the 4. And that's all under the square root dt. So I'll factor out the 144. That'll come out as a 12 when it pops out the square root. And it can come all the way out the integral. Then I'll have integral negative square root of 3 to positive square root of 3. Square root of 1 plus 2t squared plus t to the 4 dt. So this is where we're at. And this happens to be an even function, so I could apply a symmetry trick here if I wanted to make my life easier. This function is definitely even, so I could call this 2 times the integral from 0 to 3, root 3. The 2 and the 12 will interact. So I'll end up with 24 integral 0 to root 3. And then let's see what we can do with this. 1 plus 2t squared plus t to the 4. Does that look like anything you guys recognize? Looks familiar to me. Does anybody see it? Does anybody see a way to factor this? Good, it's 1 plus t squared quantity squared. A squared plus 2ab plus b squared is a plus b squared. So this is 1 plus t squared squared. That's 24 integral 0 to root 3 square root of 1 plus t squared squared. And the outer square here and the square root can cancel. So this is 24 integral 0 to the square root of 3, 1 plus t squared dt. Who would have guessed that this would come out so nice? My antiderivative from here is trivial. That's t minus t cubed over 3, evaluated from 0 to root 3. So I have 24 times, at the upper bound, square root of 3 minus the square root of 3 cubed all over 3. And that second piece can be cleaned up a bit. It's 24 times root 3. If you take root 3 and you cube it, you get root 3 times root 3 times root 3. The first two of which, root 3 times root 3, are equal to 3. And you can cancel that with the 3 down here. So you just end up with a square root of 3, right? Root 3 cubed over 3 is just root 3. Oh, wait, let me see something here. I'm actually suspicious of this now. Root 3. Is this 0? I'm nervous now. This shouldn't be 0, right? But it looks like it might be. That would be a problem. That is an even function, right? Maybe my symmetry argument gave me some trouble. Root 3 cubed. Let me just be sure. Root 3 times root 3 times root 3 all over 3 is definitely 3 root 3 over 3, right? You can cancel, cancel. Oh, thank you. This is a plus. Thank you, thank you. I got scared for a minute there. Okay, plus root 3. Thanks, Maggie. Yeah. There's no reason for that plus to become a minus when we integrate. That's a plus. All right, much better. Okay. So we end up with 48 times root 3. Beautiful. All right. So yeah, that is the arc length of this one loop. Now, I think the challenge here is in discovering the loop, right? And to get this without some sort of graphing utility would be tricky. I have no problem with you using Desmos to explore these things, as long as you come back and make sense of them. Questions on this fellow? All right, I got to get running. I have another class that starts right now. So I hope you guys have a good rest of your day. I will get this uploaded as soon as I can. And if you need anything, don't hesitate to ask. Take care, guys.